Hi everyone, I am Dhara Thakkar and today I'll be presenting my work on the minimal faithful permutation degree of groups without abelian normal subgroups, and this is a joint work with Bireswar Das. So in group theory, Cayley's theorem says that every finite group G is isomorphic to a subgroup of some symmetric group, or equivalently we can also say that we have an faithful homomorphism from uh, G to Sn. The minimal faithful permutation degree, noted as μg, is the least positive integer m such that there is a faithful homomorphism phi from G to Sn. For example, for an abelian group G, we can decompose it as a cyclic vectors. Then μg is the sum of the order of those cyclic vectors in its decomposition. Also, if G is an alternating group an, then we know that μg is n. So in this talk, we will consider this problem, which is called the minimal faithful permutation degree problem. We call it as mean per tick, where we have given a group G as an input. It is given by a generating set, say T. And the question is, we want to find mu G, the least positive integer m, such that G could be embedded into Sm. So this parameter mu g has been well studied from a mathematics perspective, but it has been not explored from an algorithmic or complexity theoretic perspective. Also, this could be interesting to study because it might be possible to show that group isomorphism problem in the multiplication table could be easier than the mean per degree problem. And the group isomorphism problem in the succinct representation, that means when it is given by generating set, uh, the mean per degree problem could be easier than the group isomorphism problem in this representation. This is not yet known, but uh, it looks like this could be possible to show. Also, when we work with permutation groups, there are certain uh, cases when we could not use all the permutation group algorithms for the quotient group itself, because there might be certain quotient which might have the permutation minimal permutation degree exponentially larger than the group. So we could not represent certain types of quotient in general. That's why we are interested in this problem. Uh, Before going into the detail of our result, let me show you an algorithm which is trivial to obtain. So the parameter μg has an equivalent definition. You don't need to understand all this notation, but what we can say is that we want to find mu g. We can first find all the subgroup lattice of a group G, and then from all the subgroup lattice, the family of subgroups, we can check for each families whether it satisfies certain condition or not, and that check is polynomial time doable. So this gives us an algorithm which has running time exponential of size of g power log mod g. So this is not efficient at all. But in our paper, we have considered the group which are groups without abelian normal subgroups. This is known as semi-simple groups in the literature. So semi-simple groups are groups without abelian normal subgroup. For example, all the non-abelian simple groups are semi-simple groups. Also, this class of semi-simple groups contain two important classes of groups, namely direct product of non-abelian simple groups and almost simple groups. Uh, Other than that, this class of semi-simple groups has been extensively studied in various algorithmic contexts. For example, um, it is known that there is a polynomial time algorithm for the group isomorphism problems when the group are semi-simple groups. Also, recently, people are studying Weiss-Fowler-Lemon algorithms for the in the context of group isomorphism problem, and where they have used semi-simple groups a lot. So this class is an interesting class if we want to study some group theoretic algorithm. Uh, Yeah, so what we have obtained is the following, that we have a group G which is given by its generating set, and G is a group without abelian normal subgroup, that is semi-simple group. Then what we have obtained is a randomized polynomial time algorithm that finds mu G. We will see the proof idea behind this theorem. We have used a theorem by Cannon, Holt, and Unger. Before uh, before stating the theorem, let me introduce this definition. So we have a group G and a minimal normal subgroup N. Then we can have an action of normalizer of S1 in G on S1, and this gives us an homomorphism from the normalizer of S1 in G to OT S1. Now we take A to be the subgroup of OT S1, which is induced by this conjugation action. So A is a quotient group, which is nothing but the image of phi. So it is normalizer of S1 in G, quotient kernel of P. That is nothing but A. So A is a quotient group. And since it is a subgroup of OT S1 and it contains S1, it is an almost simple group. Now we define mu G, comma N equals to mu of A. Now what Cannon, Holt, and Unger showed is the following, that if we have a group which is a semi-simple group, suppose its SOCL is N1 to Nr, then each Ni's are minimal normal subgroup. Suppose they have a decomposition into simple groups as follows. Then mu G is the sum of the Li times mu of GNI. And from the definition, mu of GNI is nothing but mu of AI. So to find mu G, we can find mu of AIs, and AIs are almost simple group. So this gives us a reduction from to finding mu G for a semi-simple group to find mu G for almost simple group. But here there is a catch, that the group A is not arbitrary almost simple group. It is an almost simple group that we have obtained from G, and also it is a quotient group. So since quotient group might have exponentially larger degree, this A might not be represented by its generating set. So this is a special kind of reduction where we do not even have a generating set for the group what we have obtained. We might not have a generating set for A. But yeah, still we have to find mu for this special A, almost simple group A. So the theorem reduces the following lemma, that we have given a group G and let's say N be a minimal normal subgroup of G. Then if N is non-Abelian, then there is a randomized polynomial time algorithm that computes mu Gn, which is nothing but mu A. So let us see how can we do that. To do so, we again use another result from Cannon, Holt, and Unger, which says that if A is an almost simple group, then mu of A equals to mu of S in most of the cases, except for the few cases which are mentioned in the following tables. So mostly mu of A equals to mu of S, except for the cases when our S comma A pair belongs to this table. Now, if you observe this table carefully, the first 9 groups are of constant order. So it is easy to check all the conditions whether A satisfies the condition corresponding condition or not, and we can handle such cases, right? But the difficult part is that how do we see whether our S comma A pair belongs to this table or not when S is one of these 7 groups. So that is the next step. Uh, so if you so let us recall that we want to show that we can find mu of A in randomized polynomial time. So as we have seen from the table that mu of A is nothing but mu of S1. We have a pair which is S1 comma A, except for the cases which is mentioned in the table. So what we can do, we can first check whether S1 is isomorphic to one of the simple group mentioned in the second column. If you want to see, this is the second column. So there is a randomized polynomial time algorithm that can check if given a group G as a subgroup of Sn, it can check whether there is an isomorphism from G to one of these four simple group or not, and it is by Kenter and Seres. So also this algorithm returns one isomorphism if G is isomorphic to one of these simple group. Also, if G is not isomorphic to one of this simple group, we could also check whether G is isomorphic to one of this simple group of Lie type or not, because they are of order less than or equals to n to the power 9. So it is polynomially bounded. So we can just do brute force and check if there is an isomorphism from given S1 to one of these simple group or not. So task 1 could be done in randomized polynomial time. Now, task 2 is the following. Suppose we have checked whether our S1 belongs to the second column of the table or not. If yes, then we have to check the corresponding condition that our A satisfies the corresponding condition from the third column or not. Here we have used case-by-case analysis, and each case we have handled separately. For example, suppose we have S1 is isomorphic to PSLDQ. Suppose we obtained this, and since by definition A is a subgroup of odd S1, so the table entry look like this. We have a PSLDQ, and we obtained that S1 is isomorphic to PSLDQ. And now we want to check whether A satisfies this condition or not, whether A is a subgroup of P gamma LDQ or not. Also, if you observe, P gamma LDQ is a matrix group where our A is a subgroup of odd S1. So A is a permutation group, though we do not have a generating set of A, but it is a permutation group. So that is the central part of the theorem. Like how do we check the second condition that A is actually a subgroup of P gamma LDQ or not? And let me just give an outline here, and we will see the proof idea in a moment. So to do so, we have designed two algorithms, which is a crucial part. One is lifting algorithm, where we lift an automorphism of PSLDQ to an automorphism of SLDQ. And this is not trivial because here we have a quotient group and we want to lift a map from a quotient group to an actual group, and that is not usually doable. Also, we also need a recognition algorithm where we have given an automorphism of SL of the special linear group. Also, that automorphism is specified on a special type of generating set, and we want to check its type, like what type of automorphism it is. Uh, we will see that in a moment. So that is the outline. So let me just give a proof sketch of the lemma. As we have seen, suppose from the Cantor-Seres algorithm, we obtain that S1 is isomorphic to PSLDQ. This algorithm also returns a map from S1 to PSLDQ, say ISO. Now, A is the image of the conjugation action. So let's say A is a generating set. A could be represented as a generating set CG1 to CGT. Again, we cannot use this generating set in the part of algorithm, but to understand the proof mathematically, suppose A could be represented as follows. Using this ISO map, we can find A prime. A prime is a subgroup of odd PSLDQ, and it is generated by lambda gi, where lambda gi is the composition of ISO CGI and ISO inverse. Now, once we have this A prime, we now want to use the representation of A prime into automorphism of SL, and there we need this lifting algorithm, which says that for any automorphism in the PSLDQ, which is specified on a special type of generating set, we can find an automorphism alpha of odd SLDQ such that lambda equals to alpha bar. So from this lifting algorithm, we can find A prime, the group A prime, which is alpha G1 to alpha GT, and now it is the subgroup of odd SLDQ. So our A was a subgroup of odd S1, while we obtained A prime, A double prime, which is now a subgroup of odd SLDQ. So now we have a subgroup of automorphism of some nice matrix group, which is SLDQ. Okay, so once we do so, now it is known that every automorphism of SLDQ can be decomposed as these four types, which is either an inner automorphism or a diagonal automorphism or filled or a graph automorphism. I am not going into the definition of these four, but any automorphism could be decomposed as an automorphism, as a composition of these four automorphisms. Now, if you remember, our goal was to check whether A contained in the P gamma LDQ or not. Now, it is known that P gamma LDQ could be seen as a subgroup of odd SLDQ, and it contains certain special type of automorphism. Like, it is known that automorphisms that does not contain any graph automorphism in its decomposition, those automorphisms form a group and it is isomorphic to P gamma LDQ. Now, if we want to see whether our A double prime is a subgroup of P gamma LDQ or not, we want to recognize what are the type of these alpha GIs. And there we need a recognition algorithm. So here, what this algorithm does, so we have given an automorphism of SLDQ. It is specified on some special generating set of SLDQ, and the property of that special generating set has been crucially used to design this algorithm. So once we have this setup, what we have done is that there is a polynomial time algorithm to check if alpha is an inner automorphism or diagonal automorphism. Now, this recognition algorithm crucially uses certain theorems from representation theory, for example, Schur's lemma, and also the correctness of this algorithm depends on the Schur's lemma, and also it uses Gaussian elimination algorithm. Now, suppose we have this recognition algorithm. Now, what we can do for each I, we consider the composition of these three automorphism: alpha GI, then filled automorphism, and graph automorphism. Now, in polynomial time, we can check the type of this composition map. It is an automorphism of SLDQ, and we can check the type of this composition map. Once we have the type of that composition map, we can know the decomposition of alpha GI, and we can also know the value of T double prime. If in the decomposition of alpha GI, the value of T double prime is 0, then we know that alpha GI does not contain graph automorphism in its decomposition, and that's why we know that it is in P gamma LDQ. So we will do this procedure for all alpha GIs for all T double prime and T prime, and we will be able to check whether our A double prime is actually a subgroup of P gamma LDQ or not. Now, if A is a subgroup of P gamma LDQ, then we know that it is not belongs to the table, and so mu of G comma n is nothing but mu of A, which is mu of S1. Otherwise, it is belongs to the table, and that's why from the table mu of A1 is nothing, mu of A is nothing but 2 times mu of S1. So this could be, so all the steps could be done in randomized polynomial time, and that is the case when S1 is isomorphic to PSLDQ. The cases when S1 is isomorphic to one of these group P omega plus PSP or P omega plus 2D3, those cases also could be handled separately, and where the thing which could be useful is that all this group have are matrix group, so they have a nice structure to work with. The case which is quite different than what we have seen is the following: when S1 is isomorphic to one of these group, which is G23E, F42E, and E6Q. These are the simple groups of Lie type, and here we do not have any matrix representation of simple groups of Lie type. So that's that cases needs to be handled separately from what we have seen. But here we have used the Chevalier presentation of this group, and using this Chevalier presentation, we have checked whether our S1 comma A pair belongs to the table or not. So that is the proof sketch of the lemma, and all the cases has been handled in randomized polynomial time. So this algorithm is randomized polynomial time. Other than that, we have also shown that the decision version of the mean per degree problem is in NP, even when the input group is represented as a permutation group by a generating set. Also, when the group is represented by its scalar table, we have shown that the mean per degree problem is in a D space log cube mod G. And when a permutation group G is a primitive permutation group, then we show that there is a quasi-polynomial time algorithm, quasi-poly in the degree of the group, which is n, that finds mu G, when G is primitive permutation group. So to conclude the talk, what we have seen is the randomized polynomial time algorithm that solves mean per degree problem for semi-simple groups. There are certain open problems. For example, one open natural question could be, can we cope with the randomness in our algorithm? Also, can we design a randomized polynomial time algorithm that solves the mean per degree problem for general permutation group and not just semi-simple groups? Or whether GI could be studied or could be shown that it is reduces to mean per degree. That is an interesting open problem. Yeah, that is all. Thank you.